Hello.
Hello.
Hi. Because your number is not there, so we could not put you in the WhatsApp group.
Oh, it's okay. But I'm the last presenter, right?
Before the keynote speaker.
Ah, yes. Yes. Okay.
I
Thank
was
you.
confused that whether you're pre-video or you are going to be live.
Live, live. I'll do it live.
Welcome. Thank you.
Okay.
Assalamualaikum, Prof. Welcome. So our evaluators are not here. Presenters, two presenters are already here.
Two presenters are already here. We have one, one, two. So we are going to wait until everybody is here, right?
At least Prof evaluators. We cannot start
Is
the.
evaluator.
Yeah.
I'm sorry to ask, who is our evaluator?
Dr. Yasmin, you,
Assalamualaikum.
and
I'm
Dr.
Yasmin.
Leo.
Yes.
Yes.
Dr. Prof. Zuraida, you are also an evaluator.
Evaluator?
Yeah.
I missed that one. Sorry, a little bit busy these days.
Okay, I'll tell you
Okay,
that.
before we start,
I will send you the form.
what is
I will
okay?
send you
Thank
the
you.
Google form.
All right. Thank you very much. So, meaning that we have two evaluators, right? Me and Dr. Yasmin. All right. So we have Shamala here. Shamala, how are you?
Hi, Prof. I'm good. How are you?
Fine. But we're supposed to have invited speaker first, right?
Yes, I'm before the invited speaker.
Yeah, before.
Prof,
Yeah.
the first presenter is Miss Suzaimi. After that, all presenters first and invited speaker last.
Miss Suzaimi, I thought you're also
She's
the
here.
IT committee member, right?
Yes.
So that's
But she's today working as presenter.
Yeah, I'm multitasking today.
You're multitasking. Yeah,
Yes.
it's good. It's good. Because we need young people who are multitasking. Because this is the last day and today is Friday, so we do it a little bit santai. It's okay for you, Shamala, that Yasmin? Don't worry.
Yeah, okay. I'm okay.
So that when you are happy,
Another
get,
presenter is
what we call it, pissed out of you.
Assalamualaikum. Have a good evening, all.
Iman. Welcome.
All right. How are you, Brother Muhammad? Dr. Muhammad?
Yeah. Muhammad Iman. Yeah.
All
Just
right.
call me Iman.
All right. Okay. So we are 5 minutes to 2. So how about we want to start it now? Are you okay if we start now?
No, Prof. Another evaluator.
Another
Dr.
evaluator?
Leo. Yeah.
Dr. Leo, is it?
We are first. Okay. We are first.
Miss Afrin, are we going to take the photo session first or?
Yes, after the announcement, we can go for photo session.
Dr. Leo
I
still?
just traced.
Yeah. I'm sorry. Yeah, I received the what we call it the text for the conference, how to handle the things. But I'm asking the organizer, is it okay? I'm not reading the text and we use it just in the sometime mode, Miss Afrin, the Afrin. Are you okay with that?
It is. There are some attendants. You just say in your words, no problem.
Yeah, of course. I will say a few words before that,
Yeah.
but
Just
I'm not
your words
following
is
because
fine.
I'm the kind of not really
Yeah.
following.
Yes. Completely.
All right. Kamala is here, Suzaini is here, and we wait for Dr. Young.
Our session, I have text Dr. Leo. Our session starts at 2, so we can wait for another 3 minutes.
It's okay. It's okay.
Okay, that's okay.
Because we are a little bit early. You don't mind, Afrin, if I ask you, you already sent the oh, I have the evaluation links. It's okay. I have already. Sister Noalia has already sent it to me. Dr. Noalia, is it?
Okay, okay, okay.
Maybe if you don't mind, can I just directly share my slides because I'm the first presenter?
Yeah,
Or you need to wait?
I think you can go ahead. Or
Suzaimi, there will be photo session first.
oh, okay.
Oh yeah, sorry.
You want to try?
Yeah, maybe I can try while waiting.
Yeah, you can try.
Right? Can you see the slides?
Okay. Sorry.
Okay. You can see the slides, right?
Yes, we can see.
Yes, yes.
All right, that's good. Thank you.
Sorry.
Welcome, Dr. Leo.
Haha,
So
sorry.
you can start.
Yeah.
Okay, shall we start?
Yes.
All right. Sorry for that. Okay. Alhamdulillah. Thank you very much. Assalamualaikum warahmatullah and a very good afternoon, my dear brothers and sisters, ladies and gentlemen. We are going to begin our sessions, and I would like to seek for your kind cooperation to avoid any virtual disturbance during the live broadcast sessions. But before that, first of all, we would like to thank the organizing committee for organizing this first international conference on nanocatalysts. And then we would like to, what we call it, if you have any questions, the conference resource personnel are ready to attend you at the reception desk. Thank you for your kind corporations. So Afrin, am I right? Am I read out the right text? But before, for the first presenters, we would like to welcome Sister Madam Suzaimi, right? Sister Suzaimi Johari, with the title of Recent Advances in the Base Catalytic. Sorry, no, how to pronounce this?
No. Yeah, Nova Nego.
Novel.
Nego.
I know that I'm getting younger and younger. Novel condensations. All right. Without further ado, and I would like to invite you. Tafadhal
Should
mashkura.
we take the photo first?
Oh, sorry for that. Okay. Okay, Afrin, can we have Bay? Can you open your camera so that we can take our photo? All right. Nice to meet you, Dr. Bay.
Hi, Prof. Nice to meet you too.
So 1, 2, 3. Another one. Done.
All right.
Thank you all.
All right, you may share your presentation now, Madam Susanne.
Okay, can you see my
Okay.
slides?
Okay. Yeah.
All right, clear? The sound is clear?
Yes.
Okay, Assalamualaikum and a very good afternoon. Thank you to Prof. Zuraida for the introduction and also the chairperson for today's session. To all panels and the audience for today. So my name is Suzaimi binti Johari. So I'm a PhD student in Nanotech, University Malaya. So the title of my presentation today is the recent advance in the base catalytic noble condensation reaction. So first for the introduction, as we know, over the years, the awareness of developing green synthetic methods in chemical processes has been increased. So in order to achieve the requirements of green chemistry, one of the fundamental principle is to use catalyst in the reaction process. Meaning that when you use a catalyst, instead of the stoichiometric number of reagents, the reaction is milder and the reaction time is more shorter. And of course, the catalyst can be recycled. And as a result, these organic reactions can be considerably improved by carefully designing and choosing the right heterogeneous catalyst instead of homogeneous catalysis. And for your information also, in the chemical process industry, base catalysts in organic reactions are extremely important. So among the base catalyzed reactions, the noble condensation reaction is one of the most important reaction to produce this olefinic compound, or we call it as alpha beta unsaturated compound. And this noble condensation consists of the reaction between the active methylene compounds and with the carbonic compounds, for example, like ketones or aldehydes under weak basis condition. And for decades, these classic organic reactions has been effectively used in numerous of applications, for example, in the synthesis of the intermediate or the end product for pharmaceuticals, perfumes, industries, cosmetic industries, polymers, and also the agricultural industries. And traditionally, this reaction is frequently used of piperidine as the organocatalyst and together with the pyridine as the solvent. And however, the usage of this pyridine and also the piperidine both are not convenient from many angles, like environmental health and safety, due to its carcinogenic effect, hazardous nature, and complexity in handling at the bulk scale. So owing to its very frequent utilization in organic synthesis, this novel condensation has spurred to continuous investigation aimed to find new, more efficient and green catalysts. So because of the wide usage of the novel condensation reaction, especially in the drug and pharmaceutical fields, it eventually contributed to the huge amount of waste, as we can see in the table 1 here. The pharmaceutical sectors contributed around 25 to 100 kilogram of waste per kilogram of drug. And this figure is quite concerning because the pharmaceutical sectors or industry is one of the most important sectors of the world economy, accounting for US dollar of 856 billion in 2010. And as a result of this, new and greener approaches of performing this noble condensation reaction are required for the development of ecologically responsible products and chemical processes. And over the years, various well-defined and also selective heterogeneous catalysts have been developed in novel condensation reaction. However, most of the catalysts have been dominated by the metal-based compound. So although this metal-based compound as catalyst gave very high efficiency, these metal-containing catalysts have significant environmental effects. As we know, it's very high price, gas poisoning susceptibility, poor durability, and also low selectivity. Thus, we select metal-free catalysts, which are relatively a new type of green catalytic material and crucial for both environmental remediation and also in large-scale applications. So in the slide, as you can see, it's shown the variety of the metal-free nitrogen-based catalysts that have been used so far in noble condensation reaction. For example, like the ionic liquids, the organocatalyst, a simple small compound, uh, carbon-based catalysts, for example, like the microporous carbon nitride, gravitic carbon nitride, the polymers containing the nitrogen-based catalyst, and also the bio-based catalyst, for example, the chitosan, the enzymes, and so on. So yes, for this section, I would just want to share the recent advance that have been conducted in the novel condensation using different kind of catalysts. I mean the metal-free nitrogen-based catalysts in the novel condensation reaction. For example, this publication of this previous work recently have been published by Vinu, and this author using the mesoporous carbon nitride, and the work is showing a very good GC or gas chromatographic yield, which indicated when using uh, this kind of active methylene compound, it gave very high yield, around 90%. But however, when this reaction conducted using this kind of active methylene compound, it's only producing around 30% of yield. And also, it's facing some disadvantages from this work because it required inert condition, which is very sensitive to air and moisture, and also, as I mentioned, it produced quite low yield for melanate derivative products, and also the substrate used for this novel condensation reaction is quite limited. Also, we can see here another different kind of metal-free catalyst have been used recently in 2020, using the hybrid mesoporous silica. Yeah, the same trend also can be seen in this work, where the catalytic activity was low when the less reactive methylene compounds are used, and also a very strict reaction condition for the preparation of the catalyst. And also this also recent work have been done by Dakshirmurthy in 2020. Uh, this work using a bio-based type of catalyst, also containing a very high nitrogen content in the catalyst. However, it's still the limitation of the active methylene compound used in this reaction, and also the variety of the substrate group gave quite not very high in the yield. This is also one type of the catalyst that have been used. One of the type of ionic liquids. So as we know, ionic liquids is known with the tedious preparation because it's considered of multiple steps of synthetic methods. And for this work, it's also involved not only the multiple steps of the preparation, but it also involves the toxic reagent in the synthesis preparation. We're using the dichlorodimethyl and also pyridine. And this kind of arrangement or catalyst, although it shown quite satisfying results, and it's isolated, not in gas chromatography here, but still it's not applicable in industry or in large scale. And the last one is the type of polymeric mesoporous based catalyst, also been used in the previous work. However, again, the use of the toxic reagents, for example, the formaldehyde, and a very long reaction time for the catalyst preparation is the advantage of this work. And also, as we can see, the year is being reported as a gas chromatography, not in a isolated year. And again, the limitation of the substrate scope used in this novo-Nagel condensation reaction. So typically, from the previous work, typically the novo-Nagel condensation reaction is conducted using any kind of carbonic compound, and also very active methylene group. However, when we conducted, or when the previous work conducted using this kind of methylene group, the yield would be very, very less. So what we're going to propose in this work is to prepare a catalyst that easy in preparation, very cost effective, and also having a high catalytic utility for the novo-Nagel condensation. So this is actually a preliminary work or the results of my current work. So where we currently have been synthesizing two type of catalysts containing two imidazole, one with the methyl group at the C2 carbon and one without the methyl group at the C2 carbon. So what we have found is it's a very high yield has been produced, and very high purity of catalyst 1 have been produced. And when we check for the thermal stability of the catalyst, and it can be stable until around 300 degrees C. And because of the crystalline structure that we've obtained from this synthesis, we will be investigated this catalyst for the single crystallography analysis. And from the thermal properties analysis also, we already confirm the melting point of this catalyst is around 81 to 83 degrees C. And also, okay, so this is the result for the NMR, which have been shown the high purity of the compound produced. As we can see here, is the attributed to the hydrogen in the imidazole, and these two peak attributed to the CH, the H from these two carbon here in the aliphatic site. So this is same also goes to this carbon NMR for this catalyst. It shows very high purity in the compound by not producing any solvent in this area of peak. And also for the synthesis of the catalyst 2, interestingly, the catalyst 2 have been found in liquid compared to catalyst 1, where we found it in solid. But this one is obtained in liquid, but however, it's also thermally stable until 300 degrees C. And for this kind of catalyst, it's applicable for solventless novo-Nagel condensation reaction. And these are the results for the animal result to confirm the structure of this catalyst 2. And we can found here because of the there's no CH2 in this C2 carbon, so the the 2 peak here is attributed to this 4 and 5 hydrogen at the C45 carbon in the imidazole ring. So this uh, 1 and 2 peak is attributed with the aliphatic side, and this very sharp and large high peak is attributed to the hydrogen in the CH3 compound. So this also indicated the results from the carbon NMR of the catalyst 2, and you can see that still there is a little solvent found in the NMR, but however we are trying now to try to make it crystallize, or maybe we can at least to reduce this amount of solvent. However, the rest of the peak seems to be a good in the match with the compound. And as I mentioned before, this work is still in a preliminary work. So, but we already reached all the characterization and synthesis of the catalyst 1 and 2, and we're hoping that we can get a better result for the characterization, especially for the purity of the catalyst 2. And if everything is okay, then we will proceed to conduct this catalyst 1 and 2 for the noble condensation reaction and improve the catalytic activity. So yes, for the conclusion, I can conclude that we have been synthesizing a novel catalyst for the noble condensation reaction, which are metal free, obtaining the high and yield and purity. Very simple, without any complicated purification method or using column or any recrystallization process, and it's a nitrogen rich organocatalyst, which is very good for the novel condensation. And we hope that this novel catalyst can improve the catalytic activity using low reactive methylene compounds. That's all from me. Thank you.
Thank you very much, Mrs. Suzaimi Jari, on her presentation on recent advances in the base catalytic Van-der condensations. So we open for the question and answer sessions. Is there any questions that you want to highlight, the clarifications or anything that you would like to ask our Madam Suzaimi?
Hi, Prof. Maybe I have one question.
Yes, go ahead, Dr. Bell.
Yeah.
Yes, Dr. Liu.
Hi, Mrs. Suzaimi.
Yes.
Thank you for the excellent presentations. Just a clarification, like have you done any yield or the study compared to the literature that you presented just now? And the yield result from your catalyst 1 and 2.
The year result, what do you mean? Sorry?
Like for example, just now you presented, right? On the literatures, the yield of it sometimes is not achieve the minimum, the optimum target. And then your catalyst and catalyst 1 and 2, have you done any like the GC yield?
Oh, not yet. Not yet.
Oh, not yet.
I'm still confirming the characterization first, and then only we proceed with the reaction. Yeah.
So, is it able to scale up into a large quantity for this
Yes.
novel catalyst?
Yes, it's scalable because when I perform in 5 gram, it can produce also around 5 gram of my catalyst. 5 gram of the precursor and produce 5 gram of my catalyst.
Okay, cool. Yeah,
Yeah.
thank you.
Thank you.
And for your NMR, if you present during the Viva, maybe you can make it clearer. The NMR result, because we can't really see the
Okay, all right. Thank
labeling
you.
on the top. Yeah, just for information. Thank you.
Thank you for your suggestion.
All right, thank you very much, Madam Suzaimi and Dr. Bay. Any other questions? Because we give you 5 minutes for the question and answer. This is out of, I have one question, if nobody asked the questions. In doing the advanced thing, how you find it is not related to the, what we call it, technical knowledge, but more to the experience, how you find the equipment per se in executing your research. Is it easy to get it, or you need to have the collaborations with other universities? Just would like to.
Okay. Okay. The advantages of my reaction or my work is we don't need very advanced equipment. So we can just do it in the lab scale using normal flask and directly check for the mixture compound using GC, or we can just isolate it using column chromatography. So we don't have any particular advanced equipment for this reaction because it's quite direct and simple, but yet it require of a quite tedious purification process.
In terms of characterizations?
The characterization at the moment is a typical characterization. For example, like NMR, FTIR, TGA, everything is available in NanoCat at the moment. Yeah.
Okay, thank you very much, Madam Suzaimi. Any other questions? One last questions. If there's no questions, so
No,
I
Prof.
okay. If there's no questions, we would like thanks again to what we call it, Dr. Madam Suzaimi. So we moving back to our next presentation. Presenter, please welcome our next presenter, our Mr. Muhammad Nur Iman Amir, with the what we call it presentations on gold nanoparticles supported on reduced graphene oxide as clean catalyst for solventless system of hydrosilylation process. Thank you. Please
Okay,
welcome our presenter.
okay, thank you to the chairperson and for the IT listener. Now I will share my pre-record presentation. Okay, I will start the presentation. Assalamualaikum and very good day to all. I'm Iman, a PhD candidate from Department of Chemistry, University Malaya. I would like to present and give an idea based on our research that use a catalyst known as a green catalyst for solventless reaction of hydrosilylation process. As we already stated here, this is our full research title. For introduction, the hydrosilylation reaction is the formation of organocylins and organosilicons products that have a variety of applications specifically in chemical industry and as intermediates in organic chemistry. So we can find it most widely used as an ingredient for cosmetics products. So we can identify it by the formation of hydrogen silicon to an unsaturated bond, as we already mentioned it here. The use of catalyst in that reaction is important, so that I choose the combination between graphene and gold nanoparticles as catalyst for hydrosilylation reaction. Why I choose graphene? Because it has a large surface area, 2D morphology structure with high dispersibility. It is an excellent choice as support material for gold nanoparticles catalyst. That, of course, to demonstrate with high catalytic activity, because the graphene has large specific surface area, the more gold nanoparticles can be attached due to the presence and an abundant amount of oxygenated functional group and heteroatom present on the surface of graphene oxide. Next, why we choose gold? Because it has more benefit and advantage to use as catalyst, that based on what we already mentioned it here. So the gold nanoparticles act as heterogeneous catalyst for the based on our research reaction, we use a substrate hydrosilane, and based on the previous study, solvents such as alcohol to give a final product that we know is siloxane. So gold nanoparticles support on the graphene is an obvious choice considering the non-catalytic activity of gold in that reaction. And gold support with graphene oxide, you can say that it is an ideal support material for that reaction because the strong adherence, the non-degradation of catalyst reactivity by the attachment process, and can offer a high specific surface area. So, based on the previous study, the use of gold carbon can be recycled at least 5 times without any metal leaching. Our target to achieve highest with optimum condition relate with the highest production while minimize the reaction time. Our research problem statement here, but we can say that most of the industrial application, the use of hydrosilylation reaction are catalyzed by the use of heavy lead transition metal complex. Of course, it's not involved with any environmental approach due to the generation of byproducts and solvent waste after the reaction. So we need to improvise this and enable a new reaction for a further improvement in the future. The novelty of research is due to the catalyst use of gold nanoparticle attached on the reduced graphene oxide as support in solventless reaction. So we can improvise the reaction conversion, minimize the time of the reaction. Of course, it is more environmental friendly due to the reduction of byproduct and avoid the use of solvent. So we can further investigate the process between solvent and solventless reaction as comparison. We proceed the hypothesis of research. This is our proposed mechanism of that reaction, starting with the use of substrate called dimethylphenylenediamine. Then the reaction of hydrosilylation undergo these parameters, and lastly we get the final product of diphenyl disiloxane. This is because it is initiated by the dehydrogenative coupling of reactant used into product and followed by the hydrolytic oxidation. We observe it is exposed by the ambient atmosphere. In the influence of the moisture to generate dehydrogenization. We achieve 3 research objectives. The first objective is by synthesis gold nanoparticles on graphene oxide. First of all, we produce the graphene oxide using improved Hammers method. And the second one, to characterize that catalyst in terms of its physiochemical, surface and morphological properties. And lastly, to investigate that catalyst based on different molarity of gold solution and the reaction process condition in hydrosilylation reaction. We have already prepared and divided into 4 stages of our research based on the methodology as we want to explain it here. For the first stage is the synthesis of graphene oxide using improved Hammers method. Proceed with the second stage is the synthesis of our catalyst by using one-pot reaction method between gold precursor and graphene oxide. The catalyst has been characterized using this instrument analysis. And the third stage is the catalytic reaction of hydrosilylation based on the prepared catalyst on the second stage before. So we are doing comparison between solvent and solventless reaction. And lastly, the stage 4 here is we want to investigate the catalyst for the reaction based on the different gold nanoparticles concentration that attach on the reduced graphene oxide surface. The final product of the reaction has been characterized by using this instrument analysis. Proceed with catalyst characterization. What we can observe based on FTIR analysis here is the comparison between graphite, the catalyst used for the reaction, and graphene oxide. So we can see the intensity of the catalyst decrease dramatically or even disappear after the synthesis process that undergo the reduction process. So you can see the hydroxyl, carbonyl, and hydroxyl composite decrease dramatically that indicate the transformation of graphene oxide into reduced graphene oxide. While for the FTIR analysis with different concentration use of gold nanoparticles on the surface of reduced graphene oxide, what we can confirm that based on the carbonyl and hydroxyl functional group, what we can observe that while using the higher in concentration is interfere due to the constant concentration of trisodium citrate during the synthesis process. So this finding clearly confirms the surface of reduced graphene oxide, which contain most of the oxygen functionalities, were successfully removed or reduced by that trisodium citrate. Based on the XRD analysis between the catalyst used for the reaction and graphene oxide, what we already analyzed here, there is no diffraction peak of GO observed on the catalyst sample here. This is due to the transformation of graphene oxide into reduced graphene oxide during the synthesis that undergo reduction process, while for the gold nanoparticles diffraction peak with standard Bragg reflection, we already observed it here. And we continue the XRD analysis that combined together with PSAM and EDS results here based on the different concentration of gold used for the catalyst samples. And what we can show here, the surface image of PSAM and EDS have a clear difference in morphology and based on elemental analysis. This indicates that the abundance amount of gold nanoparticles was seen at higher concentration compared to less concentration. We found that also the most optimized catalyst used for the hydrosilylation reaction is for the 0.4 millimolar concentration of the catalyst. Rather than that, based on this XRD analysis, we found that when we using higher in concentration of gold to give smaller in particle size of the samples compared to the less concentration. This is due to the amount of citrate used during the synthesis process that saturated and utilized more in higher of concentration in gold. Lastly, we want to explain the result of the hydrosilylation reaction here. What we can say here, the reaction with different molarity of catalyst analysis is confirmed by the reaction of the substrate used transformed into the final product was slow within 1 hour, so that the highest and the most optimized catalyst achieved by the sample of 0.4 millimolar concentration of gold nanoparticles. Therefore, we suggest the reaction pathway should be the dehydrogenative coupling. We have further the hydrosilylation reaction analysis within 1 hour, and we are doing a comparison between the GO material alone and the catalyst that undergo solventless and solvent reaction. We found that the GO alone has no reactivity due to the inactive material used, while for the solventless only can give 30% combustion, and the highest with 100% reactivity done by the solvent reaction. Next, the solventless reaction was further by using optimized catalyst, and it completely react 100% conversion within 3 hours. We finalized that the confirmation of final product through the GCMS analysis. We confirm the final product is known as diphenyl disiloxane. For a conclusion, to conclude our research, we have done the synthesis process of the GO material, and furthermore, to produce the catalyst that used for the reaction based on the characterization analysis that we already done and explained before, so that the use of the GO to support the gold nanoparticles, these catalysts are efficient to promote the dehydrogenating coupling of the substrate used for the hydrosilylation reaction, and to obtain the final product of disiloxane by using the most optimized catalyst samples. This catalyst can generate the reaction by the solventless. Thank you for your attention and listen to our research presentation. That's all.
Thank you very much, Mr. Muhammad Nuriman. So I would like to ask any questions from the floor. Dr. B, want to ask any questions?
May I know the potential applications in the industrial, like for example, the chemical industrial for these catalysts?
Okay. They use for the industry, you mean?
Yeah.
Yes, to avoid the byproduct for sure it is a solventless reaction, because it is a green chemistry concept, so that we can find out more to find a to minimum the time consumed during the reaction. So we need to minimize it. For sure, for solventless, it can shorten the time, but we want to go to the chemistry, green chemistry. So the solventless still need to be find the optimum time for that. Is it answering your question, Dr. Liu?
Muted. Sorry. You mean this the green catalyst, right, in your presentations?
Yeah.
Yeah. So that means the compound is safe to use. Is there any toxicity effect for the high concentration or high amount of a usage?
High amount of catalyst or what?
Yeah.
Yeah.
Is that any side effect of, if we use it for a high amount, and because you mean here is a green catalyst and then we use a green method,
Yeah, I already find out the optimum amount of the gold catalyst attached on the reduced graphene oxide, so that the optimum and the best for the catalyst use is 0.4 millimolar. that is the best for the catalyst to achieve the highest potential activity. And for the next the reaction itself, I will still further investigate it.
Yeah, thank you for the answer.
Thank you.
Okay, thank you, brother Dr. Mr. Muhammad. Any other questions?
Prof, I have
Yes.
one question.
Yeah, go ahead, Dr. Afi.
No, from the question answer, Dr. Yasmin have asked,
No,
may I know the significant novelty of this work compared to other research work?
For sure, I use the advantage of using the solventless reaction by comparing with the solvent, because the solvent is using it will produce a byproduct. So that I approach to the green chemistry concept. So by using the solventless reaction, that is my novelty there. And then for the goal itself, the catalyst itself, I used to find the most optimized catalyst of gold attached on the reduced graphene oxide.
I hope, Dr. Yasmin, that answers you. Suzaimi, you can go on.
Yes, yes, Mr. Iman. Thank you so much for your answer.
Okay.
It's in
Sami, you
English.
want to ask or you want me to read from here?
Okay, I will ask the question. Thank you, Mr. Iman, for the presentation. I just want to know, just now you shown in your slides the highest
Okay.
conversion is for the solventless, right?
No, for
The
sure,
solvent.
the solvent is the
Okay.
we can achieve the shorter time compared to solventless, but we need to further investigate the solventless to be the achieve optimum 100% of conversion.
Okay. For the solvent condition, what is the optimized reaction condition? I mean the
The conversion,
moles, or yeah, other than the time, is there any optimized condition that you use to get the highest conversion for that reaction?
I just use the optimize of the catalyst 0.4 millimolar of gold attached on the reduced graphene oxide. So I use that optimum catalyst on the uh, on the solvent reaction.
So you just optimize the molar,
The,
the catalyst loading and the time, right?
yeah.
Thank you, thank you.
And comparison between solvent and solvents. That's
I believe that is last questions or any other questions. One last one that I will allow.
Okay, I wanted to ask, does this hydrosalination reaction help the marine life?
again.
Because
Miss,
normally we know the cosmetics are causing harm to marine life, right?
okay.
Does this reduce that problem?
Still in, yeah, for sure. The This is the organics compound that used as ingredients to the cosmetics products, but for sure it has a toxicity to the environment. For sure, it's already stated on the use of the amount, the minimum amount to use for the before we uh, to go to the environment. So we need to the standard I already uh, mentioned the amount
Yeah. Okay,
based on
understood,
that.
understood.
Based on it, yes.
Thank you, thank you.
Thank you. No questions, right? So if there is no questions, thank you very much, Mr. Muhammad Nuriman.
Thank you.
So we would like to call another presenter, Ms. Shamala Gauri Krishnan, with the presentations of synthesis of magnetic base catalyst from industrial waste for transesterifications of palm oil. Without further ado, yeah, go ahead, Ms. Shamala.
Thank you, Prof.
A very good afternoon to our fellow researchers and everyone. I'm Shamla Gauri from University Tenaga Nasional. Today, I would like to present my topic on synthesis of magnetic base catalyst from industrial waste for trans-esterification of palm oil. This will be my presentation outline. From introduction, I'll be explaining on the problem statement, objective, methodology, results and discussion, conclusion, acknowledgement and the reference. To begin with, as we all know, Malaysia is one of the largest producer in agricultural waste. We do have industrial waste, and this industrial waste have been producing extensively in Malaysia. And according to the Department of Statistics Malaysia, these industrial waste have been produced 2.3 million in 2020, and it is mainly from power plant, metal refinery, chemical industry, and electrics and electronics. One of the industrial waste is the carbide lime waste, which is most largely generated as scheduled waste, which is the byproduct from the acetylene gas industry, rich in calcium hydroxide, which is mainly used in agricultural sector, road constructions, and wastewater treatment. And what is heterogeneous catalyst? Heterogeneous catalyst can be distinguished by the different phase because it forms in a solid, which is homogeneous catalyst forms in a liquid. So these heterogeneous catalysts, we can use a support material to produce, and this support material we can even source as a waste from waste materials. And as we all know, calcium oxide is the most common heterogeneous catalyst used. And whereas the magnetic catalyst, as an added advantage, it can be magnetically separated from the reaction mixture, which we can exclude the separation process by using the conventional method, which is the filtration method or centrifuge method, which may consume more time, and magnetic separation may consume a lesser time. And trans-esterification is one of the chemical reactions to produce a biodiesel, and it uses refined oil or any deacidified oil to produce biodiesel and a glycerol for byproduct. And the most common homogeneous base catalyst used is sodium hydroxide and potassium hydroxide. Based on the literature review, we discovered there are two main problems. Firstly is the effect of catalyst in a trans-esterification reaction, where homogeneous catalyst is difficult to remove from the reaction mixture because it presents in the same form, whereas the base catalyst, when we use a high acid value oil to produce a biodiesel, it may cause saponification process, where it will reduce the production yield. Whereas the second problem is the utilization of industrial waste. We are generating a large scheduled industrial waste annually, but it has a minimal utilization. And based on the statistical data, we found that in 2019 there have been 4 million plus tons have been producing. And this improper disposal may cause environmental problem or health issues. Based on the discussed problem statement, we initiate to use this waste material to produce and to synthesize and to characterize CLW, which is a carbide lime waste supported magnetic base catalyst, and to evaluate the catalytic efficiency in biodiesel production. Here is the flow of methodology. We have executed a simple methodology where we use the carbide lime waste. We calcine as a pre-treatment process to calcine, and then we use the calcined carbide lime waste to prepare the magnetic solid base catalyst by the one-step impregnation method, and we characterize it And later, we studied the efficiency in the trans-acidification reaction. In trans-acidification reaction, we have a section on the effect of a reaction parameter to study the catalytic effect. Here is the results and discussion divided into 3 sections. The first section will be the catalyst characterization. The second section is on trans-acidification, followed by the product characterization. In the first stage of results and discussion, we began with the basicity tests on the solid base catalyst we produced, and we found that this catalyst actually generates a very strong base. With the help of Hammond indicator, we detected the catalyst has a strong basicity at the pH range from 18.4 to 22.3, which is considered as a strong base. And this results actually in line with our CO2 TPD analysis, where it shows the catalyst has a very high basicity of 3637.2 micromole per gram. So at this range of temperature between, we found that the range of temperature, which is between 600 to 800, actually generates a very strong basic site. In the morphology analysis, at the low magnification range, we found that the particles are in irregular distribution with crystal-like formation. But at the higher magnification, we found that the particles are formed in a cluster formation, and the small spherical shapes explains the catalyst is the particles have been embedded on the CO2, calcined carbide lime waste. Followed by the EDX analysis, we found that this catalyst has a high composition of calcium and oxygen, followed by iron and also sulfur. We do have sulfur, and by the molar ratio of iron and calcium and oxygen, we found that this catalyst is composed of ferric-based iron-based calcium oxide and calcium oxide. This was confirmed when we did XRD analysis, where we found the formation of a megamite particle, which is the iron oxide formation in the cubic structure, followed by the cubic calcium oxide formation. And this catalyst has a surface area of 18.54 meters square per gram, followed by the pore volume of 0.142, and it has a larger pore size, which is 30.77 nanometer, which explains the catalyst as a mesoporous particle, which helps to the active site to be easily accessible for the reactant and produce a high yield. And followed by that, since our catalyst is a magnetic-based catalyst, so we have conducted the magnetism study, and we found that the catalyst has 6.61 EMU per gram, where the catalyst can be removed by using a strong magnet. And based on the literature review, we found that when the magnetization value is more than 4, the catalyst can be separated by using a magnet. In FGI analysis, we found that the presence of calcium oxide at the band 878, followed by the iron oxide formation, and at the peak of 675 and 597. In the trans-acidification reaction, we studied the efficiency of the catalyst in 3 different parameters. The first parameter is the percentage of the catalyst loading, where we found that the catalyst has a better performance as the catalyst loading increases, but the optimized level was found at the 6% of catalyst loading, where the 85.8% were achieved. But after further increase in the catalyst loading, we found that the biodiesel yield reduced. The second parameter is the methanol to oil molar ratio, where we found the highest yield was achieved at the 12 to 1 methanol to oleic acid, oil molar ratio, which with 88.3%. Lastly is the effect on the reaction time, where we found the 3 hours reaction was the best reaction to produce the highest yield of 90.5%. And with the optimization study by one factor at a time method, we found that this catalyst had a higher yield of 90.5% at optimized reaction temperature of 6 weight% catalyst loading, 12 to 1 methanol to oil molar ratio, and at 60 degree Celsius for 3 hours of reaction time. Followed by the product characterization phase, where we found that the catalyzed sample, actually we have a carbonyl group which is in circle, and we found that the catalyst was able to catalyze the palm oil and produce a biodiesel. In the comparison of the physiochemical characteristic between the other literature studies, we found that our catalyst has a better performance in terms of the physiochemical properties, and it's a comparable biodiesel yield, which we can accept it at a moderate reaction temperature and shorter duration. In conclusion, carbide lime waste supported magnetic base catalyst was successfully prepared by one-step impregnation method, and we have characterized by various analysis. And the highest biodiesel yield was achieved at 90.5% with optimized reaction condition at 6 weight% catalyst loading, 12 to 1 methanol to oil molar ratio at 60 degrees Celsius for 3 hours. And we can derive that industrial waste magnetic base catalyst can be a promising catalyst in biodiesel production. I would like to acknowledge the fund provided by the Ministry of Education, and the raw material which was provided by Mineral Research Center from the Department of Mineral and Geoscience Malaysia, and my university for the support and the facilities. List of key references. Thank you.
Okay, thank you very much, Ms. Shamala Gauri Krishnan, with the paper title Synthesis of Magnetic Base Catalyst from Industrial Waste for Transesterifications of Palm Oil. So we open for the question and answer.
Maybe I start first.
All right.
Thank you, Prof. Thank you for the excellent talk, and Shamala. I just have one question on it. You compare the physical chemical properties of the magnetic base catalyst, right, in your presentations?
Correct.
Yeah, and then but there's no magnetism properties in the table.
Yes, I can explain that actually. When I did my literature review, actually all these catalysts, they did prepare magnetic catalyst, but whereby their magnetism is either they don't report after the catalyst preparation, so there might be some reduction in their magnetism, so they did not report it. So that is why I compared, but we still managed to get a 6.61. Maybe it's in a way we are saying that our catalyst is performing better than the other literature. Yeah.
So none of the literature reported the magnetism properties? Because for me, 6.61 actually is quite low though, but I'm not sure for your applications.
Yes, I understand, because of course we also looked into the magnetism study, but when we did, we found that we got it as 6.61. So maybe in my literature review, we think that there might be some other particles interference that they may contribute to the reduction in the magnetism. So that is why we got it. But anyhow, after the reaction, we still able to secrete, or we are able to separate the catalyst completely. So there was no any sediment formed after the reaction.
Okay, cool. Thank you.
Thank you.
Okay, thank you, Dr. Bay. Any other questions from the floor?
Yes, I would like to extend the question from this slide. May I know,
Okay.
Ms. Shamala, why is the other research, I mean, the other references that has been highlighted here, there's no magnetism value being showed here? What is the reason?
No, yeah, I did mention earlier because the magnetism, they did how to say, they did a magnetic catalyst, they prepared a magnetic catalyst, but in their literature review, but they, I mean, sorry, in their paper, they did not report after the catalyst preparation. They just prepared, they just, how to say, they just published for the initial stage of the preparation. It's not the final stage. So that is why we found that most of the literature which uses the CaO as a raw material did not provide us the final magnetism value.
All right, okay. So what will be the most parameters which give an impact towards your study against the others?
Uh, Parameter as in for the catalyst preparation or the
Both.
both. Okay. If let's say for us the most because we are producing a biodiesel, so for us the most important parameter is the basicity. So we have to make our catalyst as a strong basicity, and followed by our surface area, because we need to have the interactions between the catalyst and the reactant. So to in order for us to produce a higher yield.
So does it mean the surface area has to be smallest to achieve
Uh,
your target?
No, because based on our study, what we generated, we found that this 18.54 is able for it's like it really applied to us to produce a 90.5% of catalyst sorry of biodiesel yield.
All right, okay.
Okay, thank you, Ms. Shamala. We have questions from Ros Fazila Abdullah. The question is, she mentioned that thank you for interesting presentations. How about the reusability of the catalyst? Did the magnetic properties sustain after a few reactions?
Okay, for the reusability study, we because we are on the we did on the first part of the screening of the catalyst. So on the reusability, we have not moved into that, but we will look it into in the future. But we found that the catalyst after the first reaction, we able to separate completely. So later we may reuse it to study on the to further study on that.
Okay, is Ms. Shamala answering your questions, Ros Fazila? Okay, is there any other questions? If there is no questions, we come to invited speakers. Am I right, Afri?
Yes, Prof. No question anymore, but we have a change. Our
Yeah,
invited speaker name is changed. I think you
yeah.
know already.
Okay, yeah, I'm aware about that. We are going to have our invited speakers number 36, Aini Shahira. Am I right? Aini Shahira, with the title, is Aini Dr. Aini Shahira is here? Seems like that we don't have her yet here.
Yes, she's here. Can you, Miss Aini Shaira, can you please ask for sharing audio and video? So you just can be on the screen. Now we will play the recorded.
Okay, thank you very much, Dr. Bay. Oh, she is. So that Aini Shahira will present a paper with the title of Advanced Oxidation Process AOP for Toxic Organic Pollutant Removal. Okay, she is sharing her presentations now. So the Anisha will be given 25 minutes for the presentations and 5 minutes for question and answer.
Hello.
Yes,
Okay. Sorry.
the presentation is just have a problem with the presentation.
Uh, can everyone see my screen?
Can IT committee help Ani Shahira for the presentations? Okay, it's okay now.
Okay. All right. Sorry.
It's okay.
Okay. So is the screen okay?
Yes, it is okay, IT Shahira.
Okay. So I'll start my presentation. So good evening, everyone. My name is Aini Shahira. So I'll be presenting in place of my supervisor, Dr. Shazwan Hanani. But my title today would be Advanced Oxidation Process (AOP) for Toxic Organic Pollutant Removal. Okay, so so moving on to the introduction. Wastewater has been a global-wide concern, and it has a big impact on the environment and living organisms, especially humans, and also the aquatic biota. Wastewater contains many things such as high concentration of solids, dissolved particulate matter, microorganisms, nutrients, heavy metals, micropollutants, and other organic and inorganic pollutants. So most of these pollutants are harmful to the living organisms and should be treated properly. But otherwise, we and other essential organisms will suffer as we cannot access the safe and clean water, which is our daily life necessity. So in conjunction to that, water demand was reported to increase proportionally to the dramatic increase of population. Um, And this condition is predicted to worsen by 2050 due to many factors. So the increasing water pollution and depletion of water sources also add up to this concern. While in Malaysia, the water quality deteriorates due to these three factors: urban development, forest degradation, and also agriculture, mainly as reported by Kamara and colleagues in 2019. So this should be a concern to the country as the major water resources come from the river where most of the pollution set in. So this calls for proper wastewater treatment and management to provide consumers clean and safe water as well as to save the environment and other living organisms. Kam and Gosh described that wastewater can be effectively treated by degradation of pollutants and mineralization. But the conversion of pollutants into more stable oxidation state can also be done if necessary to ensure that the end products are harmless and the water can be safely distributed to the consumers. So advanced oxidation processes, AOPs, can contribute to this initiative as they use radicals that act as oxidants. So these radicals will degrade the pollutants efficiently and speed up the oxidation or the degradation process of the pollutants. So this process can also combine different parameters to increase the degradation rate. For example, by using catalysts like irradiation and also ozone. In fact, many studies have used UV with catalysts to degrade different types of pollutants, especially the industrial effluents. As known, the industrial effluents contain many toxic compounds that are released into the water sources, and this can cause health complications and environmental issues caused by ineffectively treated water. So there are different types of AOPs that can be used for wastewater treatment. So and these are the different types of AOPs that are founded as to date. Different processes affect differently on wastewater pollutants. So in other words, the types of pollutants require different types of processes, and only the most suitable process can effectively degrade targeted pollutants and treat wastewater. So the fundamental of AOPs require radicals to act as oxidants to oxidize or degrade pollutants completely or convert it into more stable, harmless state. So let's look to the first AOP, which is the ozone base AOP. So ozone is often used as oxidant and disinfectant in wastewater treatment. Ozone produces hydroxyl radicals due to disintegration, and it is also very selective, so it only attacks the electron-rich functional groups such as aromatic rings, double bonds, and also amines. Reaction of ozone with organic matters will yield radical ions byproducts, but ozonation or secondary effluents can generate more radicals. So the more formation of radicals, the higher the oxidation rate of pollutants, which means more pollutants can be degraded. More radical formation can also be achieved by increasing the pH and coupling the ozone with other factors such as hydrogen peroxide, UV light irradiation, and also catalysts. So there are two different types of catalytic ozonation, which are homo and heterogeneous catalytic ozonation. These two are distinguished by their solubility in water. The second one is the UV-based AOP, which involves UV irradiation or radical generators that can be coupled with the UV irradiation itself. These radical generators, such as hydrogen peroxide, ozone, chlorine, and peroxydisulfate (PDS), will generate different types of radicals, such as hydroxyl radicals, sulfate radicals, and different chloride radical species. But it turns out that the process of UV with ozone has relatively higher cost than the process of UV with hydrogen peroxide. This is because it requires more electrical energy for UV lamps and also ozone generator. And on another note, sulfate radicals and chloride radical species are alternatives for hydroxyl radicals. So we can decide whichever we prefer. Either you can use sulfate or hydroxyl radicals since they are alternative for each other. But sulfate radicals are more effective than hydroxyl radicals since they can dissolve more organic matter. This is because their nature of having higher selectivity than hydroxyl. So next is the electrochemical AOP, EAOP. So this process requires an electrochemical setup with different potential electrodes. So during its oxidation process, the radicals are generated on the surface of the electrode, which is known as direct electron oxidation process, or the radicals can be generated in a bulk solution, which is called an indirect electron oxidation process. Some of the most common used electrodes are BDD and also doped titanium dioxide. So since diamond is not a good conductor, it is doped with boron with better conductivity to be used as the electrode. While titanium dioxide, on the other hand, is readily a good conductor, but it is still doped to increase its efficiency in degrading pollutants. Electrochemical AOP is considered less tedious since there are no further steps required, such as water polishing and sludge disposal, since there will be no formation of sludge after the process. And lastly is the catalytic AOP. In a catalytic oxidation process, a potential catalyst is used to generate radical ions. For example, iron can be used to degrade pollutants as a catalyst. So this process is called a Fenton process. Study carried out in 2014 recorded that the catalytic activity of the iron was at maximum at pH 3 when the ferric oxyhydroxide precipitates. So during the Fenton process, the ferrous ions will react with hydrogen peroxide to generate hydroxyl radicals. However, excessive hydrogen peroxide can lead to reduction of iron 3 to iron 2, which will affect the generation of radical ions. Photofenton, on the other hand, differ from the Fenton process as it requires like activated catalyst. So in this photocatalytic AOP, UV or visible light is used to accelerate the Fenton process. So this promising technology, the AOPs, has brought to my current project, which is the study of the formation effects of the nitrogen and copper embedded titanium dioxide nanotubes on simazine photodegradation performance. So this is why simazine is the targeted pollutant. So simazine is an organic toxic herbicide that was found in wastewater and other water sources. Simazine is also one of the herbicides that are commonly used in agricultural. So simazine that are absorbed by the soil will eventually end up in our water sources. So this will affect our health and also the aquatic biota. Simazine is also classified as toxic herbicide by WHO, so it needs to be removed effectively to ensure the safety of the organisms and also the environment. Other studies also reveal that simazine can damage the neurons of mammals and was found toxic to the soil and also aquatic biota. So this study aims to remove simazine via photodegradation using UV light irradiation and titanium dioxide nanotubes as the photocatalyst. Okay. So this is the summarized methodology of the project. There are three stages primarily: the anodization, doping, and photodegradation of simazine under UV light irradiation. So during anodization, the first stage, an oxide layer will be formed on the titanium foil surface, as you can see on the image on the left. So in the presence of fluoride ions, the nanotubes will be formed by forming holes on the oxide layer. So the figure on the right shows the cross-section of nanotubes under SEM in different types of electrolytes, but containing fluoride ions and also applied with different voltages. So as you can see, results show that the nanotubes are formed effectively with distinct features in ethylene glycol, e.g. electrolyte containing ammonium fluoride at 25 volts. It can also be observed that the nanotubes holes and the diameters are consistent compared to the other images, which show irregular shapes. Next is doping of titanium dioxide nanotubes with dopants. So the figure above shows the representation of doped titanium dioxide nanotubes. The figures below show the SEM images and EDX results of the titanium dioxide doped with copper. So on the left side of the figure, it can be observed the dopants, which is the copper, which appear in white color, whereas the right image shows the ADX scan present, which shows the present elements under the SEM, which are titanium oxide and also copper. The last stage is the Simonsen photodegradation under UV light irradiation. This result shows the trend in concentration of rhodamine B over time. So as you can see, the concentration of RHB is constant without catalyst, while the concentration of RHB decreases over time using different catalysts. This is another study of photodegradation of triazines, which are atrazine, simazine, and bromocrine. So these these herbicides are tested in distilled water of pH 7.1 without and with hydrogen peroxide. So in this literature, it shows that the results, so in this literature review, the result shows that the pesticides are completely degraded. 90% pesticides are completely degraded after 24 hours without hydrogen peroxide. And with hydrogen peroxide, 80% of pesticides are completely degraded only after 6 hours. So this shows that the addition of the hydrogen peroxide is critical to the degradation of the herbicides. Okay, so this study is significant to many, um, such as the society as well as the wastewater treatment system. This study also reveals that the toxicity of simazine can affect the health of many organisms, including plants and animals. Other than that, this study can also benefit the university as well as the country in the development of clean drinking water. And finally, this study can also aid in building the fundamentals of titanium dioxide nanotubes modification and the development of sustainable water technology. So that's all for my presentation. Thank you.
Thank you, Ms. Aini Shahira, for the presentations. So we are open to the floor to ask the questions. Is there any questions from the floor? Okay, if there is any no questions, I would like to ask. You did mention about the applications. Beside the one that you mentioned, what are the applications from your research project?
Can you repeat that?
Other applications. What are your applications from
Other applications than wastewater treatment. Sorry, I think I'm breaking up. Can you repeat the question?
I'll repeat the question. Sorry. Because my could be the internet problems.
The question Prof asked is that what are the applications of your product?
Okay.
Am I right?
Yes. Yeah, you can hear me, yeah, Afrin, because it can
Yes,
see
clear.
because it's written here internet unstable.
No, I can
Okay,
hear you clearly.
okay.
Miss Ain, I think she's not here.
Yeah, I think I think the connection's not that good. So the committee, shall we proceed to announce the winner, or we will vote for Aini Shahira?
When she comes, we can continue with the question answer. And if anyone want to ask any question, you can also write in the chat. She can answer by text.
Mm. All right.
Yeah.
So I believe there's no questions, Afrin, Dr. Afrin.
Yes, Prof.
I believe there is no questions right now.
Right now, no question.
Alright. So shall we
Yes,
announce?
we can continue.
So I'm very honored to announce the best presenter for the sessions, session 5, which is goes to Miss Shamala Gauri.
Thank you, Prof. Thank you so much.
All right. So I think that is what we call it. Uh, the end of the presentations. So I passed over. We would like to thank very much for the organizer, and then on behalf of, we would like also to thank all the presenters for the good presentations, and I pass over to the committee for that. Thank you very much.
Thank you all.
Okay, thank you all.
Okay, it's okay, Sister Aini, for the answer the line. Thank you very much. Bye.
Okay, thank you.
Thank
Bye.
you. Bye.
We have, Prof. We all can proceed to the ending ceremony.
Okay.
Right, Iman? We have ending ceremony now.
At
Yeah.
4 o'clock,
Yeah.
right?
Yes, ending ceremony. At
Yes.
4 p.m.
Yes.
So
Okay.
I'm sorry for that because I need to join another meeting. Thank you very much for the
No
organization.
problem. No problem. Thank you for your time, Prof.
Thank you, Dr.
Okay.
Yasmin.
Welcome.
Okay, clear. Thank you.
Shuzaimi, you will go to.
Yeah, I'm here still.
Okay.
I'm doing my lab work. Sorry.
Oh, you are doing the lab.
Yeah.
Do you know my lab? Is it open?
Oh, I didn't check just now. I didn't see.
Yesterday
Why?
also I saw your lab got the same problem.
Oh, really?
Yeah, yesterday in the IT committee you.
Oh, not my lab. Not my lab. It's Leah lab.
Oh, so this is that door is okay now.
I don't know. I think there's somebody wants to enter the lab.
Same my problem. Somebody wants to enter the lab. Try wrong key. My lock broken, and the key is there also.
Yeah.
Yeah. Okay. Thank you, Suzaimi.
Okay. Bye.
End of this long sitting.
Yeah, I want to rest.
Yeah, true.
Oh my god.
Okay, bye.
Bye.